Alrighty, so this video we're going to work out some example problems for the ideal gas law and of course those relationships that come from the ideal gas law. We learned last time the equation PV equals nRT or PV equals nKT, where this is the ideal gas law. This is a model which basically relates the characteristics of a gas, the pressure, the volume, and the temperature. Now, the difference between these two equations, of course, is purely based on what knowledge you have about the gas. Do you know how much gas you have in terms of the number of molecules, which that's the N, so molecules, or do you know how much gas there is based on the number of moles? Where moles is like, how many dozens do you have? But instead of dozens, it's Avogadro's number. And so if you know the number of molecules, you'd use nKT. If you know the number of moles, you'd use nRT. But they're the same equation at their heart. The constants, so R, the ideal or universal gas constant, is 8.314. And K, the Boltzmann constant, is 1.38 times 10 to the minus 23. Okay, so those are just constants. They're just numbers you need for these equations. But when you're given a problem and you're working with an ideal gas, then you're going to choose one of these two equations based on, as I said, do you know the number of molecules or do you know the number of moles? Now, extending these gives us a relationship between these three characteristics. And so there's a nice little formula. It says P1 V1 over T1 equals P2 V2 over T2. And what this allows you to do is if you change the volume or you change the temperature, you want to know how the pressure changes. Or maybe you change the pressure, you keep the temperature the same, and you want to know what happens to the volume. Things like this. How do they relate to each other, and how do they change if you affect some of the other ones? From this is the main one, you can get the other ones just by taking things constant. For instance, we have P1 V1 equals P2 V2. And this is exactly the same as the other, except where T1 and T2 are the same number. So that is, you don't change the temperature. The temperature remains constant. Then T1 is the same as T2, and they cancel out. So all that's left is pressure and volume. Of course, the same can go P1 over T1 equals P2 over T2. This happens when you keep the volume the same. And then lastly, V1 over T1 is V2 over T2. And this happens when the pressure is the same. So this main equation gives you all three of these. Now I just remember the main one, and when I'm given my problem, I just cross out whichever characteristic I'm not working with in that problem. Instead of trying to remember all three of these other, the gray ones, I just remember the black one. So now let's go ahead and use these equations to work out a few problems. All right, so here's our first example. 5 moles of gas is placed in a spherical chamber of radius 0.5 meters. If it is at 100 degrees Celsius, what is the pressure of the gas? Okay. Well, I know the equation I'd like to use. Let's go ahead and see what we know. What are we given? Number one, we're given the number of moles, N, equals 5. We're given a radius of 0.5. We're given a temperature of 100 Celsius. And we want to know the pressure. Well, this problem is not asking us if we change the temperature, what happens to the pressure or anything like that. We're just told, here's a gas, it's in this container, tell me about the pressure. So that means I'm going to use the equation PV equals nRT, the ideal gas law itself. I'm using the little n, the nRT version, because I'm given moles in this problem. So, in order to solve this, pressure is nRT over V. So I need the number of moles N, I need the ideal gas constant, the universal gas constant, which I know, I need the temperature, and I need the volume. I have everything except the volume. I don't know the volume here. But I do know something about the chamber itself, something about the thing you've placed the gas in, and it is a sphere with a certain radius. So I know I can get the volume by saying volume of a sphere is 4/3 pi r cubed. So 4/3 pi times 0.5 cubed, that gives us 0.524 cubic meters. So now I know the volume. The other thing I need, however, the temperature. Remember, in physics, when we use an equation that has temperature in it, if it's purely the temperature and not the change in temperature, I need Kelvin. But I've given degrees Celsius, so I have to convert. So I need the temperature in Kelvin as the temperature in Celsius plus 273. So 100 plus 273 is 373 Kelvin. And now I have everything I need, so I could place it all in my equation. N is 5. R, remember, is 8.314. The temperature in Kelvin, 373. All divided by the volume, 0.524. And what do I get? 29613.53 pascals. Or if you want the scientific notation, 2.96 times 10 to the 1, 2, 3, 4 Pascal. And so that's how you do an ideal gas law problem. You're given some information about this gas. We know the ideal gas law, which relates all the different characteristics together, and we plug our numbers in, making sure we're in the right units. Remember, everything's meters, cubic meters, pascals, Kelvin, things like this. We get our equation, solve for the unknown, whatever the thing is I'm looking for, and then I plug all my numbers in, and I'll get my answer. All right, let's try another example. Example 2. 2 moles of a monatomic gas at 100 degrees Celsius and 1 times 10 to the 5th pascals is heated to 300 degrees Celsius. What will be its new its new pressure, sorry. Alrighty, so let's see what we have here. We're given the number of moles, N is 2. We're given an initial temperature, T1 is 100 degrees Celsius. We're given a pressure, 1 times 10 to the 5th pascals. We're given a final temperature, 300 degrees C. And I'm looking for the final pressure. So, now that I know what's given in the problem, I start to figure out what equation will I use here. Will I use the ideal gas law itself? No, I wouldn't, because this problem is talking about changing a characteristic, and if that characteristic changes, how do the other characteristics change? So rather than using the ideal gas law proper, I'm going to use the little relationship that says P1 V1 over T1 is P2 V2 over T2. Now, note in this problem, I'm not told anything about the volume. I'm not saying the volume changes. I just have the gas sitting there in whatever container it's in, and I do these things. So that tells me that the volume's not going to change. So I get rid of the volume. I don't worry about it. And that leaves me with the new equation, P1 over T1 is P2 over T2. So that's what I want to do. Before I can do it, I need to make sure all my units are correct. For pressure, I have to be in pascals. Thankfully, I am. And temperature, I have to be in Kelvin. Remember, even though I am changing temperatures, the equation itself doesn't have change in temperature. It just has a T1 and a T2, but I'm not subtracting them. So don't confuse when I say, if you're told you have a change in temperature, you could use Celsius. That's not what I mean here. Here we are changing the temperature, but the equation itself doesn't have something like delta T or T final minus T initial or something like that. That's not in this problem. Note that wherever temperature is in this problem, it's just the temperature by itself. And then on the other side of the equation, there's another temperature by itself. So because of that, I have to use Kelvin. I'm not in Kelvin initially, so let me go ahead and convert. T1 is 100 Celsius plus 273, which is 373. And T2 started at 300, and I add 273, so that gives me 573. Now we're in Kelvin, and so now we could go ahead and use our equation. We started with a pressure 1 times 10 to the 5th, divided by T1, which is 373 Kelvin, equals P2, which is what I'm looking for, over T2, which is 573 Kelvin. So solve for P2. P2 is 1 times 10 to the 5th times 573 divided by 373, and I get 1.54 times 10 to the 5 pascals. Of course, if you want to write out the decimal, 153619, that's fine, but a lot of times, especially with thermodynamics, people use scientific notation for their answers. It just makes it a little neater, so it's not this big, huge, long number. And so there's an example where we use the little characteristic relationship equation. And you see, even though when I write the equation, I have all three characteristics, P, V, and T, given a problem that only uses two, I could just cancel out the other one. No worries. So let's do one more. Example 3. You are given a gas at 4 times 10 to the 6th pascals in a spherical container whose radius is 20 centimeters. If the container grows to a new radius of, let's say, 40 centimeters, what will be the gas's pressure? Okay. So, what do we know? Well, we know we have a gas whose initial pressure, so P1, is 4 times 10 to the 6th pascals. We're given an initial radius, R1, of 20 centimeters. Then all of a sudden, the container grows and we have a new radius of 40 centimeters. And I want to know the new pressure that occurs because of it. All right, well, this, again, I will not use the ideal gas law proper because, number one, I'm told about a change in the characteristics. The container will grow, thus the volume is going to change. And because the volume changes, the pressure is going to change. So I'm going to use the relationship P1, V1 over T1 is P2, V2 over T2. Then I see that this equation, or this problem, does not ask anything about the temperature. It doesn't give the temperature. It doesn't say that the temperature changes in any way. All that I'm changing is the size of the container that the gas is placed in. And so the temperature doesn't change. I could cancel out the temperature from my equation and be left with P1V1 equals P2V2. That's the equation I want to use. What is it I'm looking for? I'm looking for P2, so I'll go ahead and solve this equation. P2 is P1 V1 over V2. I just divided the V2 over. So that's what I need. I need the original pressure, I need the original volume, and I need the final volume. Well, I have the original pressure, so that's good, but I don't have the volumes yet. What I know is the radius of the container and its shape, which is a sphere. So I need to use that information to calculate the volume. So how do we do it? Well, the volume of a sphere is 4/3 pi r cubed. However, notice that our radii here are in centimeters, and that's bad, so I need to convert them to meters. 20 centimeters is 0.2, 40 centimeters is 0.4. You have to be in meters. Do not leave centimeters. In fact, I can't even think of a single time in this semester where you're given centimeters and you have to keep it in centimeters. So please, any question you get, unless I specify for some reason, any question you get, if the information is in centimeters, you convert it to meters. So here we had to convert, but the conversion's easy. Centimeters to meters, you just move the decimal place over twice. All right, so volume 1, 4/3 times pi times 0.2 cubed. And this gives us 0.0335. And we do the same for V2. V2 is 4/3 pi r2 cubed. So 4/3 times pi times 0.4 cubed, which gives me 0.268. All right, now we're good to go. I have the original pressure, I have the two different volumes, now I can solve my problem. So P2 equals P1, 4 times 10 to the 6th, V1, 0.0335, divided by V2, 0.268, and that gives us 5 times 10 to the 1, 2, 3, 4, 5. 500,000. So you can see all of these problems seem to be done the same way. You're given some information. We have a relationship between the three characteristics, P, V, and T. You read through the question, you write down the information given, and then you see, do I use the ideal gas law, which is, here is a gas in a certain state, tell me about one of the characteristics. Or do we use the relationship? Here's a gas, we change something about the gas, how does this other thing change? Once you know which of those two equations to use, you figure out, do you need all three characteristics or just two of them? You look at the information you were given. Are they all at the right units? Are they all in meters, Kelvin, things like this? If not, you can do all your conversions. Once all that's done, it's just a matter of feeding those numbers into the equation you've chosen and calculate the unknown you're looking for. When you give an answer, I don't care how you present it to me, whether you give it to me as a scientific notation or you give it to me as a full decimal. I'll be fine either way. If you're doing something like scientific notation, be sure to give enough decimal places so I know, don't do 3 times 10 to the 5th if it's 3.47, Give enough decimal places so I can see what your answer is. Don't round it. Here I rounded 5 times 10 to the 5th. That's because the actual answer was 500,000. So, 5.00, I just wrote it as 5. But if it was 5.78, 578,000, I would have said 5.78 times 10 to the 5th. But anyway, that is the examples for this particular topic. I hope this is understandable. Definitely practice a few, get the hang of it. And of course, if you have any questions, as usual, please email me. I'll be happy to answer whatever I can, help you through these problems. Until next time.